What's up, everyone? Kelly Heim, integratedpharmacology.com. This module is all about mechanisms of action, or MOAs. And you might think you know the MOA for a variety of compounds and a lot of medicines. If you've done a lot of reading, you may think you understand the MOA. So there are a few things you need to keep in mind whenever you're reading about MOA, whether it's in PubMed or a journal article or promotional literature. So this module will walk you through common pitfalls, things you really need to keep in mind to avoid making assumptions and arriving at false conclusions. So let's get right into it. So let's say I'm interested in learning about how curcumin works. When I enter curcumin in PubMed or Google Scholar, and I read a few abstracts, I spend about an hour reading the abstracts. This is what I come up with. The first thing to keep in mind is not all of these are relevant. Some of these are just not going to happen clinically, and some of them probably will happen clinically. And it's very likely to depend on how much you give, dosage, context, etc. So I'm going to talk about these variables. Many of the so-called mechanisms of action that you will detect in the literature are actually false. Searching PubMed for curcumin and trying to figure out, what does curcumin do? How does it work? It's a daunting task, considering that nearly 12,000 publications are indexed on PubMed to date. Your first inclination might be to filter the results so that you only see human clinical trials, and that's certainly not a bad idea. The only limitation of the human clinical trials is that they can't really show you what the mechanism of action is. So that would be the same with any compound. Human clinical trials really can't tell you how something's working. They can only tell you whether something is working and at what dose and for what specific indication. You might want to just stick to human clinical trials if that's all you're interested in. However, since we're on the subject of mechanisms of action, I'm going to show you a few things to keep in mind when you're searching literature and learning more about natural products and how they work. So for curcumin, about 60% of the total publications are in vitro, or in another preclinical model. Rats and mice comprise roughly 30% of the total publications. So we're looking at 89% of the publications on curcumin are preclinical. And it would be a mistake to throw them out and ignore them, because they tell us a lot about how curcumin might work. So how does curcumin work? Well, it depends, and that's going to be the answer for anything. It's going to be the answer for any compound you enter into a search. So keep the data in a proper context. Figure out what it is you're looking for. Are you interested in inflammation? Are you interested in inflammation in muscle, in the gut, in the brain? So you really have to narrow your search to that particular context. We have trillions of cells in our bodies, and they all have the same DNA, your DNA. But obviously they look different, they function differently, and that's because of epigenetic differences. So the epigenome refers to chromatin marks that change the expression pattern of genes. It also refers to the DNA methylation pattern, which also changes the expression of genes. So because of these differences, not all cells express the same transcription factors and the same components of a pathway. Some components might be missing. With regard to transcription factors, like the vitamin D receptor, for example, the target genes depend on the cell type. Because of these epigenetic differences, even though you might have the same ligand bound to the receptor, you might have vitamin D or a deltanoid or derivative of vitamin D bound to that receptor, even though it's the same ligand in different cell types, that set of genes that's regulated by the vitamin D receptor is different. And therefore, the mechanism of action of vitamin D in fat cells versus macrophages is going to be different. So another pitfall is using the wrong compound. And researchers often do use the wrong compound to interrogate the mechanism of action. It seems silly. Why would you make that mistake? It just seems like something a scientist would never do. But we're learning more about natural products all the time. And one of the things that we're learning is that they are metabolized to very different compounds. This isn't the case for most compounds, but for some, like flavonoids, quercetin being a great example, the parent compound is extensively metabolized by gut bacteria to derivatives that bear no structural or functional resemblance to the parent compound. So we kind of have to start all over again To study quercetin and figure out how it works, we have to study these metabolites. And studies looking at the mechanism of the metabolites of quercetin still remain few and far between. Another common pitfall is to overlook potency. By potency, I'm referring to the inhibitory concentration or the effective concentration that's required to hit that target of interest. IC50 refers to the concentration required for 50% inhibition of your target. EC50, or effective concentration, is the same exact principle. It's just not inhibition per se. Quercetin is widely used for seasonal allergies, and its proposed mechanism is stabilization of the mast cell membrane, which reduces the degranulation of histamine. The concentrations required to have this effect are actually quite high. We're looking at an IC50 of 100 micromolar. Can we achieve the concentration clinically, the effective concentration that is required to execute that mechanism of action? That is the question. So concentration is everything. And if you watch the Medicine's Journey lecture, we talked about mechanism of action and all medicine being concentration dependent. So how something works depends on how much is there. Unfortunately, many polyphenols and other phytochemicals don't have very good bioavailability because the body perceives them as potential toxins and metabolizes them, sends them out of cells in a process called efflux, which we've examined in the Medicine's Journey lecture. So they are xenobiotics. The body wants to get rid of them, so the bioavailability tends to be quite low. Considering that quercetin is extensively metabolized to other compounds and its bioavailability isn't all that great, it's unlikely that you're going to achieve a high level in the body, and it calls into question whether that mechanism of action is really true. You might see blurbs in the media, headlines about new studies coming out, shedding light on how phytochemicals and natural products work. Some of these are in preclinical contexts. So here's an example of something you might see. This was a study that looked at quercetin, found that it was more effective than cromolyn, which is a pharmaceutical mast cell stabilizer, in blocking human mast cell cytokine release. But the concentration that they used was 100 micromolar. First off, you want to look for that micromolar or nanomolar concentration as soon as you look at the abstract. It's the first thing you need to look at. So anything in the micromolar range is okay. Anything in the nanomolar range is better. Most drugs and some dietary supplements fall in the nanomolar range. Picomolar is really potent and really uncommon. It's very unusual to find natural products that are that potent. Certain hormones work in picomolar ranges, like estrogen, for example, and pro-resolving mediators, which are involved in the resolution of inflammation, also work in the picomolar range. But generally, you won't encounter highly potent substances in the world of phytochemicals. So let's go back to quercetin and the mast cell membrane. We have an IC50 of 100 micromolar. Can we achieve this clinically? In human pharmacokinetic studies using quercetin supplements, the peak plasma concentration doesn't even come close to 100 micromolar. So based on this information, the mast cell stabilizing mechanism might not hold true in the clinic. And if you use quercetin successfully for seasonal allergies, it's probably working in some other way. For a mechanism of action to be real, the IC50 or EC50 should be somewhere in the low nanomolar range or below. So anything in the micromolar or millimolar range when you're dealing with natural products is questionable and possibly irrelevant. And that just means that the compound is very weak against that molecular target, and you're going to have to give a mega dose clinically to even have a chance of recapitulating that effect in the clinic. And with poorly bioavailable phytochemicals, it's even more of a long shot. Here's a study that examined resveratrol and its inhibitory properties towards eosinophils, which are involved in the allergic response. And right off the bat, you can see on the x-axis, which is a really nice shortcut when you're reading a paper, go to the figures, look at the x-axis, what does it say? So you're in the micromolar range. It's not great, it's questionable. Resveratrol is notorious for low oral bioavailability, which only makes it more difficult to achieve this inhibitory concentration clinically. On a more promising note, this was a study of a vitamin D analog and its ability to inhibit COX-2. The IC50 was 5.8 nanomolar. So in a word, that's excellent. This mechanism of action is much more likely to hold up in the clinic. This was a study on resolvins, which are derivatives of the omega-3 fatty acids involved in the resolution of the inflammatory response. And these compounds are effective in the picomolar range. So that's pretty unusual, but these are very potent compounds, and that simply means that only a small amount needs to get to the target tissue to do its job. So the mechanisms described in this study are more likely to hold up clinically. So in summary, when you're investigating mechanisms of action in the medical literature, keep these three things in mind: cell type and context, whether the compound is metabolized, and concentration, namely IC50 or EC50. You want to look for micromolar or nanomolar concentrations, preferably nanomolar, and you want to make sure that they don't deviate too far from the plasma concentrations that are achievable in the bloodstream or in the target tissue based on pharmacokinetic studies.